Right, so I hope you've all downloaded OLEX 2. Okay, from Cambridge Structural Database, and you've also downloaded Mercury as well. Now I can't run Mercury on this computer because of the administrator access and so on. Okay, but it helps if you've got Mercury open, because Mercury does a few things that OLEX 2 doesn't. It helps if you've got double screens as well. So you can have Mercury on one, OLEX 2 on the other. So OLEX 2 is a program that solves and refines, and you can produce pictures with it and so on. It essentially does everything all in the one program that combines various programs together. And you can put shells out in there if you like. There really is no need. Okay, so it comes with various tutorials and it gives you sucrose to begin with, and you can work your way through that. So the first thing to do is open the program and load up a file. You will get, if you come and see me with a memory stick, okay, because you'll need the INT file, and INT files you can't send by email because the university web service sees an instruction file and thinks it might be a virus, so I can't send it. So you need to come with a memory stick. You've got a lot of files. Okay, and the one you need is the INT file, so you open that in OLEX 2, and it doesn't look like it's done anything. Okay. To start with, I will give you a sheet, and I will give you all the files. Okay, only 4 of them could be opened in OLEX 2, but here's a whole lot of them. Okay. And I will ask you to find some data in those files. Okay. And you may have to look through a number of files to find those. Oh dear. It doesn't know what it's doing. Notepad. Okay. So we've got things like the PAR file. What's the one? One I want is actually the prep file. There we go. Okay, you can open them all with Notepad. No, it's not that one. Yeah, well this one actually will show some things. Okay, here we've got the unit cell parameters. Okay, so you can see that this is orthorhombic. We've got 3 different lengths and 3 angles of 90 degrees. And we've got the ESDs there. That's the old. So, no, this one hasn't got anything. What are we looking at? We can open the INTs file. No, that won't be any good. Okay, the HKL file is the list of the HKL reflections, and we have an intensity, and we have an ESD there as well. Okay, so that will, however many tens of thousands that is. It's telling us it's in P212121, which is orthorhombic. It's telling us in the standard setting. Okay, sometimes you get crystal structures that it's better to solve in a non-standard setting. Okay, so something like P21 upon C, which is the most common space group for compounds. Okay, you could do that as P21 upon A, P21 upon B, okay, or P21 upon C. Okay. You're just changing the axes around. Okay. It makes it more convenient to solve. Okay. It may give you better standard uncertainties. Okay. Just because of the way the mathematics of it all. Okay, but they're all this space group. They're just different settings. And you can, I think there's one as well, I2 upon C. Or I2A is a non-standard setting. So this is primitive and this is body-centered. Okay. But it's still P21 upon C. It's still that, it belongs to that family of space groups. And I did see a paper to referee a few months ago where the authors had said that when they had substituted a hydrogen atom for a methyl, they went from P21 upon C to I2A, a completely different space group. So this, obviously a different crystal structure arising from the addition of a methyl group. Well, that's not unusual. But I had to point out to them that I2A was actually just an alternative setting of P21 upon C. So in fact it was the same space group. Okay, it was a case of the paper being written by non-crystallographers. They hadn't gone and checked with their crystallographer whether it was the same or not. So that happens quite regularly. So just be aware that you may have to look up whether the space group you get is actually a standard setting or a non-standard setting. If it's a standard setting, it's going to be one of the 230. Okay, and it's going to be as written. They're all in the international tables as well. So P21 upon A will be, in the section under P21 upon C. Okay, let's look at. This is the one that perhaps most important. Okay. This is the SIF before we've done anything. Okay. It has a lot of that information. Okay, so it tells us about the crystal size, which I've actually entered. Number of formula units per unit cell. Well, that's obviously wrong. Okay, that's because we've started. And it's just sort of, I put in a formula that wasn't quite right and it's got that wrong. But that will be changed over time. When you get your files, copy them and store them somewhere safe, perhaps under a different name, because as soon as you start doing things, it overwrites everything. Okay. If you need to go back and do something again, okay, you will need your original files. If you've overwritten them, you won't have them. Okay, so save them, put them in a folder, call them something else. Or relabel the folder and label them 1, 2, whatever, and you can start all over again. Okay, so there we are. You can see that we've got an Rn value of 1.89% there. We've got a number of molecules in the unit cell is 3. Number of molecules in the asymmetric unit, Z dashed is 3/4, so something not quite right. The complete value there refers not to how complete the structure is, but how complete the data is. How much data have we collected? Okay. And that will change with space group and symmetry and so on. So what we need to do, okay, I think this is in the instructions that are on the Moodle page, is you click on work, okay, and we have 3 or 4 options there. Okay, we're going to be solving initially, so if we click on that down arrow, we get a range of options. Okay, we don't have to change anything, it's got the right space group. It's going to use OLEX 2 to solve. Okay, Superflip doesn't seem to work for me anymore. If you wanted to use shellax, that's where it would come up if you've got it downloaded and so on. Okay, and we just click solve. Simple as that. Okay, you can see it's solving. Right, and we get these brown spheres. And they indicate the positions of the electron density. Now, I think we can see that we've got something that looks a little bit hexagonal here, like a benzene. And maybe we've got another bit of a benzene over here. Okay. So what we can do is now change those from what are known as Q peaks. Q means anything, it's just electron density, to various atoms. Okay, so I can put in, if that's benzene, then okay, so we've got 6 of them joined up. This looks like a beginning of a benzene as well. Okay, we're missing one, but that may turn up later. Okay. We've solved it. We haven't refined it. We haven't gone through the whole process yet. So we go to refine, and we just click on refine. You can see there we've got spheres now that are grey. They're isotropic. Okay, it still doesn't look terribly right. We've still got brown spheres everywhere. We want to get rid of the brown spheres. We just press on Q twice, and we get rid of them. Okay, but we need them because they're telling us something. Okay, so you can see now that when I click the Q again, it put a carbon atom in this position. So we can put a carbon atom there. Okay, it looks like there might be something bonded to it here. Let's put that as a carbon, and one there. Okay. We've also got 4 things, or 6 things around the hexagon. Okay, so now those Q spheres are labelled Q1 to Q whatever. Okay. And 1 means it's got the most electron density of the Q peaks, of the Q spheres. Okay, so it's unlikely to be a hydrogen atom, it's going to be something different. Q21, on the other hand, that's likely to be a hydrogen atom, but we don't deal with that just yet. Okay, so now what we do is we press refine again. Now, you can see that these 8 carbon atoms and these 8 ones here are roughly the same size. Okay. But these ones are a lot smaller. And what does that indicate? It indicates that that atom is heavier than carbon. So what we can do is perhaps call those, let's try chlorine, shall we? We just click on those, we change them to chlorine, we refine again. Okay. Now what's happened is that all our spheres of carbon sort of disappeared, they're too small. Okay. The chlorine ones look fine. Okay. That suggests to me that chlorine is the wrong element in there. Okay, so something smaller than chlorine, get rid of those Qs. Perhaps fluorine. Okay, that's good. If we look at that, all the spheres are roughly the same size. Okay, which is an indication that we've probably got the identity of the atoms right. Right. We've got some other things to fit in there though. Okay, we've still got quite a few Q peaks. When you solve a structure, it's very often the case that the atoms that are supposed to be bonded to each other aren't actually close to each other. They're wildly different elsewhere. Which is why mercury is good. Mercury puts them in the right place to get a bond. You can do this by going to growing. Okay, broken fragments. You go atom to atom. Okay, it tends to put them in the right place. Well, it looks like we've got another hexagon here, but it's clearly in the wrong place. So maybe we need to go back to broken fragments. Okay, so refining again has actually put things in a more sensible place. We've got, if we label those Qs, okay, we can turn the labels on. Okay, Q1 is here, Q2 is there. They look like they're going to be reasonably big atoms. Okay, and then we've got some Qs here, 4, 3 possibly carbon atoms. We can try that. Okay, we'll call those carbon as well. Okay, so we've got another couple of Qs that we can put in as Cs. See what happens. Okay, it's happy with that. What we notice now is that we've got lots of Qs around the carbon atoms that look like they could be hydrogen atoms. Okay, it could be, this could be an aromatic system, it's planar, so we're going to end up with hydrogen atoms in these positions, and these Qs might indicate that. Okay, they don't look like being other carbon atoms. Okay, we could try one. Find that. Okay, it's gone far too big. Okay, so it must be a smaller atom. So we can just delete it. Okay, so we'll get rid of the Qs. No, we need the Qs. What we notice here is that this carbon atom and this carbon atom have some electron density with them. Okay. We also notice that those spheres are slightly smaller than the spheres next to them. C24 is slightly smaller than C20. That suggests that it may not be a carbon atom there. Okay, if it is a carbon atom, then it's going to be an acetylene. Okay, so we expect a hydrogen atom here, and we might see some electron density also. Something else it could be that will give us a linear bond is, of course, a cyanide, a CN, a nitrile. So maybe we should put a nitrogen in there. Okay, and in there, and we'll refine again. Take the Qs out. So that looks pretty good. All the spheres are roughly the same size. Okay. You'll notice at the top now our R1 value has gone to 6.47%. So that's pretty good. We want to be under 5. And we haven't put the hydrogen atoms in, we haven't made it anisotropic, and it's still 6.4. WR2 is 20.17. Okay. Now before we get too far, there's a couple of things we have to do. Firstly, we have to change this to actor. Okay. And the other thing is, not that one, this one, we need to put in the command list 4. This is in order for it to generate the relevant data in the CIF, the crystallographic information file. And also I put in conf as well, which gives us extra information. And we just click OK. That overwrites everything in the instruction file. Okay, so now we can, I don't like the labels being on, we can turn them off. We can refine again. If you press solve again, you'll go right back to the beginning. Okay, so we don't want to do that. Okay, so there we are. We now make it anisotropic, so we click on this ellipsoid here. It automatically refines, or if it doesn't, you just click on refine, and you can see that the R1 value has dropped. You can see that our thermal ellipsoids are looking good, they're quite small, and also they've got the longer axis in the right directions, perpendicular to the bonds. Yep. Okay, so that's looking good. We just add hydrogens, make sure add them in the right place. Again, because this is ticked, it's going to refine it automatically. So there we go, now we're down to 3.48%. So we've got 10.8% of W12. So this is working well. This is one that I know is relatively simple to solve. Okay. Now, in case we're worried that we've got the wrong space group, P212121 is a non-centrosymmetric space group, so it has a centrosymmetric partner. Okay? It will always solve in the non-centrosymmetric one, but maybe the centrosymmetric one is the correct space group. So what we do here is we go back to solve. We don't click on solve, we click on the arrow, and we click on suggest space group. Okay. And you can see down at the bottom here, possible space groups P212121, and we're 19. Class MMN, point group 2 to 2. Centrosymmetric, none. It's not giving us an option. The only one it will solve it is that. We wanted to check that, we look in Mercury and click on packing. Okay, and if the molecules are sort of overlapping, then it's obviously wrong. Okay, if they're packing together nicely and there's not a lot of space left over, okay, they're packing nicely. Okay, so we're almost there. You'll notice up here we've got a few things that are red, we've got a shift that's red. So that means that when we do the refinements, and we're set up to go through 4 least squares cycles. Okay, you can see cycles 4 there. It means that the last time we did a cycle, it moved one of the atoms 3.302 picometers or whatever. Okay, so it's not quite refined fully, so we'll refine it again. Okay, and you can see the shift has gone down, it's no longer red. We'll do it again. Okay, it's gone down. We'll do it again, it goes through 4 cycles again. Okay, and it's getting towards it. You need it to be 0. Okay, you need green. Now we need to look at a few other things. And these we can do using info. Okay. We can look at refinements, reflection statistics. Okay. We can look at the Wilson plot. Okay. And you can see that this is some values. We've got sine squared theta divided by the wavelength squared. And we've got some intensity data there. And it's telling us whether it's non-centrosymmetric or centrosymmetric. But actually it's sort of indicating it might be centrosymmetric. Okay, but it's near the middle, so we shouldn't be too worried about that. So it's a statistical analysis. Okay. We can look at the cumulative intensity. This is a similar thing. Okay, so if it follows this black line, then it's centrosymmetric. If it follows the blue line, it's non-centrosymmetric. If it's in between, then it could be either. Okay, again, it's a statistical analysis. And it looks like, well, it's close to the blue line, so we're quite happy with using a non-centrosymmetric space group. Systematic absences. Okay, this is telling us where the systematic absences are actually occurring when they should be systematically absent, so we might be getting small peaks due to some issue within the crystal or just some chemical feature. Okay. This is one that's quite interesting to look at. This is our observed scattering factor divided by the calculated scattering factor, and it should be sort of linear. If our observed and calculated are the same, we get a straight line gradient 1. This is very good. You can see we've got pretty much a straight line. Sometimes you end up with squares out here. Best thing to do is delete them. You can do it on this graph, or you can do it another way. Can't delete too many. Okay, that's a way of massaging the data. Okay, but that looks pretty good. We probably won't have to delete any. There's a few other things we can look at here as well, but this is looking all very good. I don't know what half of these things mean. Completeness. So that's, don't really use those. So those reflections that are off that one-to-one line, another way of looking at them is bad reflections. And we can omit bad reflections. Okay, so here's reflection H minus 2 bar, K 7 bar, L 22 bar. Okay, the error compared to the ESD is is quite large, okay, or not, rather than the error, it's the error compared to the intensity of the peak. So it's a small peak with a large error. We could omit that if we wanted, and just click on omit. Okay. What it's telling you here, the standard setting is it says omit all reflections where that value is greater than 10. Okay. And pretty much you can use that. I think greater than 10 doesn't matter, minus 10 or plus 10. Okay. But this is good data, okay, so we don't need to do any of this. You may need to do it for your structures. Okay. So we're almost there. I guess we ought to go into report, just to click on the green ones. Okay, this is telling us we have actually got pretty much complete when we merge the SIF. That gives us the SIF. Everything's worked out there, I think, in Crystal. Okay, I've already entered the values there. This data has already been through the absorption correction and everything else that I have to do before it's ready to be solved. Okay, so we don't need to do any of that. Now what we need to do is look at the weight. Okay, we've got everything there, we've got the hydrogen atoms. Oh, well, one thing we should do is correct the values of Z and Z dash. Okay, clearly we have got 3/4 of molecules within the unit cell. Oh, sorry, the asymmetric unit, or 3 in the unit cell, so we change that to 1 and we press OK. There we go. Press it a couple of times. It's given us the right formula now. It's given us the right value of Z, that is 4. Okay, so there's 4 asymmetric units in the unit cell. And in the asymmetric unit, there is this 1 molecule, or in fact it's 2 molecules. It's not 3/4 of a molecule. Okay, so it considers it to be the whole component. And if you've got solvent, of course, that will be part of the molecule as well. Anions and cations related similarly. Right. We now have to click on weight, and we'll refine again. Okay, notice now it's shifted a bit more because we've changed the data slightly by adding that weight. See, these values are starting to get greener. Okay, so there we are. That's it pretty much. Okay, we can check where the electron density is. Okay, there's a few spurious peaks. You know, it's where we might expect there to be electron density, close to atoms or in bonds, close to the hydrogen atoms. There's not the more transparent they are, the less the electron density. Okay, so there's not a really one big one that's sticking out. We haven't forgotten a water molecule in there or anything else. Okay, so we can just ignore those. Okay, so we're almost there. We can ignore the flat parameter. That's due to the non-centrosymmetry. Okay, so this has now generated, if we go back to that SIF, okay, you'll notice that it now has a lot bigger file. We open that. It's overwritten. So we now have the positions of the atoms put in. We have those R values incorporated. We have the parameters for the thermal ellipsoids. We have the bond distances. We have the bond angles. Okay, and then we have all the HKL values incorporated. Go right down to the bottom. There's a sort of it tells you the holes and the peaks. Remember I mentioned peaks and troughs, where we we have little bits of electron density. Okay, you can see that down there. Number of reflections and so on. Everything is listed in that CIF, that crystallographic information file. Okay, also gives us the position of all those Q atoms. So that's pretty much it. What we can do is click on report and it will generate a report. Okay, now you'll need this for your assignment. What I don't want is people to just copy and paste this. What I want you to do when you do your assignment is a little bit of introduction about what the compound is, whether it's a salt or a molecule, a little bit about the chemistry. I want you to look at a crystallographic information in a paper, preferably one of mine, okay, because, and I want you to make up a table where you put that data in. Okay, so you can put in the crystallographic data here, so it's all for Robert P21, everything's down here, our int is nicely presented, we've got our R1 values, okay, this is for all those peaks where the intensity is greater than twice the standard uncertainty, R2 value, and then for all data. Okay, so this is the number of reflections collected, and 5,625. That's the number that are independent, but all of them are observed. Okay, so it's good data, and there's 253 parameters. See that this is 10 times that. Okay, so we expect it to be so far. So you get that, and then you get a table of positions, and then you get a table of bond lengths. Again, don't just copy and paste. It's not. It's the important selected bond distances I want you to put in the table. Okay, but just copying and pasting, you're not actually thinking about which ones are important or why. Think about which ones are important. Don't put in the carbon-hydrogen distances, and you know why, or angles. And then we've got all the angles as well. These are also contained in the CIF, so you can get them out of there as well. Remember to include the ESDs, standard uncertainties, because they're important. Okay, there's an experimental that they write for you with references, so that's very helpful. I expect you to have an experimental part to your... Write it as if it were a journal article. Write it about the structure that you get. Have some discussion on what it looks like and why. Use mercury to see what it looks like when it's packing together. Are there any inter-ionic or intermolecular interactions? Are there any close distances that you want to talk about? In this case, this is actually one of Prithwish's, you probably recognises it. We've got some pi-pi stacking interactions, okay? The phenanthrene here is close to the tetrafluorophallonitrile, and they stack like this, you get columns. And that's an interesting feature. Use mercury, you can actually calculate the distance between this plane and that plane. So a lot of these things, especially if they're salts, they have lots to talk about. You can get sort of distances between the anion and the cation. Okay, you will have to use mercury to get those distances. So it's not just a simple task to do that. So there will be a bit of work in doing that. Okay, the last thing you'll need to do, what you should do is when you submit your assignment, also have some pictures. Okay, you can generate them from mercury, and you can generate them from OLEX2. OLEX2 will give you this sort of molecular structure. Mercury, you can get packing structures and everything else, so it's much better to be mercury. So you want to put some, you want a picture that shows the numbering scheme. Okay. When you talk about the C1, C2 bond distance, we need to know where C1 is and C2 is. otherwise it's meaningless. Okay, so you need one where you label things, but maybe in the packing figures you don't need to. And I should talk about how you label your structure right at the end. What you need to do is you need to go to mode, naming, number sequentially from 1. Okay, so this one looks a good place to start. So I go 1, 2, 3, 4, 5, 6. We'll call that one 7 and 8. We'll make it all logical, and we can start here. 9, 10. And we have to refine again, unfortunately, to get the numbers in. I don't mind really how you number things, but just make it logical. I don't want C1 here and C3 over there, sort of thing.
Is it clockwise or anti-clockwise?
It doesn't matter. It's up to you. If we turn it up the other way, it's the other way round. Okay? It doesn't matter. I always tend to, when I've got fluorine atoms, I tend to give them the same number as the carbon atom to which they're attached. So we start with F1, if we click it again it goes F2, F3, F5, F6, okay, and we refine again. The hydrogen atoms automatically change label depending on which carbon they're attached to, so don't worry about labelling those. Okay, and we can leave that as N1 and N2, okay, so we just refine that again. If this has gone from 0, you'll just have to refine it again. So that's what we do. Sometimes you want to remove the hydrogen atoms from your diagram. You can do that with Mercury or with this program. There we go. It hasn't actually removed the hydrogen atoms, it's just removed them from the picture. Okay, they're still in the sieve, so we can put them back in as well. Okay. That makes things less cluttered. Okay. Certainly for packing diagrams. Okay. Yeah, so when you submit your assignment, you can submit it electronically to me, send it by email. Okay. You should submit a report, which should be a Word document or a PDF or whatever. Submit your CIF file, CIF, which should have all the HKL values, and then I can see what you've done, okay, if you've done it right or not. And you'll also need to do this. And I want this file submitted as well. Okay, now this is a program on the Cambridge, on the International Union of Crystallographers website that you can use for checking your CIF, your crystal data. Okay, so I always get it as a PDF. Okay, we browse, we look at that, and we put in the CIF. Nowadays, that CIF contains the HKL values, so it gets automatically incorporated. Okay, so we want full validation. We just send it for checking, and it delivers a PDF back. Okay, so there we go, download CIF report. So there we go. And we've got some A alerts. It's telling me that the crystal description is missing. Well, that was my fault because I didn't put in that it was colourless and a block. Okay, it's telling us that the diffraction theta value is low. Okay, why is that? Well, if that happens to you, just ignore that. And it tells you what these different alert levels are. A is sort of terminal, we need to do something about it. B is it may be terminal. C is a suggestion. Okay, centre of gravity not within the unit cell, i.e. one of the molecules is sort of more out than it is in. That's just because rather than using one over here, it's used one over here. But that shows the packing better. we're missing something. We've got no flat. We've got a low free pair coverage because of various issues. Okay, so we can ignore those. And G1s are sort of things you should check. Okay, so it'll give you a list of alerts. You should look through these, especially if you've got A's and B's, because they might be terminal. You might have done something wrong. Okay, you might have to go back again. Okay. And it gives you a picture at the bottom as well. I know this one's pretty good. So, you know, it's telling us that perhaps some of the thermal ellipsoids are a little bit funny. Okay, the flat parameter's not good. Well, that's because it hasn't got any really heavy atoms in it. There's all sorts of reasons for this, pointing us towards that. Okay, so if you've got wrong assignments, if you've assigned something as a chlorine and it should be a fluorine, it'll tell you. Okay. Another way of sort of handling that is by using this brush thing here. It cleans things up. Okay, if you've got the wrong atom and it's only if it's horribly wrong, again, the right one here, or one that is closer to the atom. So if you think it's platinum and it's actually sort of fluorine, it will correct it to something that looks nearer to fluorine. So that's pretty much what you'll need to do for your assignment. Now, I think in your assignment, they've all been done before by myself, so I know they're easily solved. Okay, they might be complicated structures, but the solution and refinement is relatively easy, so there shouldn't be too many problems. It will give you a false impression of crystallography in that it's easy. You click on solve and there it is. Well, actually there's no sense of enjoyment or fulfillment for solving a crystal structure like that. Okay, it's the ones that are a bit harder where you have to spot things. Or the students told you the wrong formula that's run by another way. You know, rather than being a gallium compound, it's something like a platinum compound. There's a bit of working out, or things are on mirror planes, so it's hard. Okay, but the ones I've given you should be relatively easy. If you have before you submit it, I would, if you have any concerns about the SIF report, the SIF check report, email me with your report, because it may be that you really need to do this again. If you want to play around with it, you can do. If you want to put it in a different space group to try, feel free. That's often worthwhile. You can see what happens. Remember to save what you've done and to save your initial files, because every time it will overwrite. I think that's about it. That's what you need for your assignment. Okay, so it gives you an idea of what's used, what we do when we solve a crystal structure. Okay, what's involved, how you get to the end. Another thing you should write in your assignment is talk about the quality of the data. I've indicated it through the lectures. What parameters we look at. Are any of your thermal ellipsoids looking horrible? You might want to point that out. Okay. Remember that the formula at the top, at the beginning, might be wrong. Use your chemical nous. In the past, someone thought they had a salt. They didn't spot that it was a cation. And rather than having a bromide anion, they had a selenium atom. If you put in selenium, it actually gives you a better result than if you had bromide. It gives you a better result crystallographically, but chemically it's nonsense. You've got a cation on its own with a neutral atom. That doesn't make sense. Okay, so use your chemical knowledge, go with that. Chemical knowledge. It's a salt, there must be an anion for every cation. Okay. So if things go horribly wrong, just start again. If it doesn't solve first time, just click on solve again. And you might start to see things. Things may not appear initially. You may have to play around and start. Eventually, things arise. Okay, there's a limit to the number of cues are shown. You don't want 200 queue peaks arising when you first click solve, because that just clutter up everything. So a program will set it at about 20. You can change it if you like, set it at about 20. So if your molecule has 40 non-hydrogen atoms in it, you will only see 20 of them. So don't be surprised if everything's not there. Okay. It will eventually appear, because once you start assigning those atoms and pressing refine, it will give you 20 Qs. Okay, but as soon as you've got, say, 12 carbon atoms, you've now got 32 Qs rather than 20 to begin with. Okay, so you'll need to go through all of that. Any questions?
No.
Okay, so that's CheckSIF. I think it's all on the instructions in on the Moodle page. They were for an older version of OLEX 2, but I think they are still valid, but there might be some extra things that I've told you today that aren't there, just because it's been updated. Right.